It really is a very special pleasure for me to introduce Manu Kapur, our second keynote speaker of ICLS. The process that we went by to find keynotes, as you might imagine, is one of a consultation to talk to colleagues and get suggestions and so on. So when Peter Ryman and I were putting together the proposal idea, of course we did that. And one of the suggestions that we thought made a lot of sense was a general one, was to say, well, could we find somebody who's an early career researcher who's starting to make a significant contribution to the field. If we could find someone like that as opposed to mid-career or late career people, that might be a nice thing. So we thought that was a good idea. And then, of course, we then started to solicit some ideas for who might be a candidate to be that early career keynote speaker here at ICLS. And what was perhaps not so surprising was the name that kept popping up from various folks we talked about is the second keynote speaker we have today, Manu Kapur. Now this, for me, was particularly nice because I've actually known Manu for quite a few years now. I guess, when was the January conference? 2005 or 4? Yeah, something like that. And so at that time, Manu was just finishing up his PhD at Columbia University Teachers College and had a paper, as many of us have had, at AERA. It was grouped into a paper session, and then I was discussing on that session. And so I had the opportunity to hear about his research at that time. I don't think your kind of characterization of it as productive failure had even been articulated then. But the research that he was reporting there was very interesting, was very clear, it was very rigorously done, very thorough, very well-grounded theoretically and conceptually. One of the things that I try to communicate to my PhD students is that you're probably going to work just as hard on a not-so-great research idea as a really great research idea. So the things really come down to articulating some kind of seam in the literature, some kind of seam in what we don't know, and then finding a really interesting way to explore what that is. And what really struck me about his work at that time is that he had that knack, if you will, for finding a nice seam in the literature. But having done that, one does get data, one analyzes it, but then the process of conceptualizing it and then building on that research afterwards, the PhD, for those of you who are early career, isn't the end of what you're doing. That should be the beginning of a path of research and inquiry that kind of helps launch off your professional career. Well, clearly, Manu Kapur has done that. And the publications in the very top journals we have in the field, several of them, speaks to the impact that this research is having, the quality of it, the way the ideas are developing. And I recommend to those of you who may not know his work that well to read the early papers and the papers now. You can see a mind that's really looking at the research findings and thinking about how that might impact ways of characterizing and conceptualizing that. The way to grow our ideas over time is what science is about. And I think Manu's work is a wonderful exemplar of that process that an early career researcher can have. I guess just in closing, really let me just say that I'm actually looking forward to hearing about the latest thinking and work that you're doing, Manu, and I'm sure the rest of us will as well. So let's put our hands together and welcome Manu Kapur.
First things first, can you hear me at the back? Loud and clear? Good. All right, thank you, Michael. Let me just set this up. Okay. So, thank you for inviting me to share this work, and it's really a very humbling experience, I guess, to be standing in front of giants and delivering this. So I was understandably a little nervous, and last week Jeremy Rochelle was in Singapore. We went out to dinner and asked Jeremy, hey, any words of wisdom? And he said, look, Manu, a keynote is supposed to give the conference something to talk about. And so if you do a good job, we'll have something to talk about. But if you're an abject failure, like a Bollywood flop, we'll have that to talk about. So either way, you'll have something to talk about. And so it was very reassuring. Thank you, Jeremy. And so, yeah, so while I preach productive failure, I certainly do not want to practice it. Okay, so to start things off, I thought I might share with you how I got to think about productive failure, the role of failure, right from the early days when I myself was a student, and when I became a teacher, and then as a graduate student, and now, starting this research or building upon this research. So we go way back to 1996 when I was a final year student in mechanical engineering in NUS, National University of Singapore, and I was searching for an honors thesis. And I eventually settled on this thesis on solving a couple of differential equations in aerodynamics. That was my thesis. And my supervisor said, "Oh, you know what, just go and try and solve it mathematically and come back in a month." I said, okay. I went back, tried a couple of ways, didn't work. Went back and said, "Look, I tried these ways." He said, "Oh, that's good. Have you tried something else?" I said, "Okay, I'll go back and try that as well." So I went back, it again didn't work. I was back in his office in a month's time. And that cycle kept on repeating for 3-4 months, and I was beginning to get worried. Simply because I wanted to graduate and I was not going anywhere with the project. And so I told him, "Look, maybe I should change. Maybe there's something wrong with me, I know a lot of you want to answer that question. Please don't. And he said, "Look, don't worry about it. This problem cannot be solved mathematically." I said, "What? I've gone at it for 4 months and now you're telling me that this problem cannot be solved mathematically?" So yeah, it's a complex dynamical problem and it does not admit a mathematical solution. I said, "You could have told me that 4 months ago." And he said, "Yeah, but now you understand the problem. Now let's look at the solution." And the solution is computational in nature. And because you worked different ways in which mathematics actually does not work, you know where mathematics ends and computation starts. And I think that was the key, and that was a very deep learning experience in failure that sort of shaped my thinking. And he was right. Within a couple of months, the model was done and dusted, and I graduated. And then I became a teacher. But I took that experience with me into my teaching, and it was just an informal and intuitive way of saying, "Oh, well, before I teach something, I want to give you a couple of challenges and see how you approach it. I know you're not going to be able to solve it, but I still think that you should do it." And I kept that with my 12th grade students year on year for the 4 or 5 years that I taught in Singapore. Then I went to graduate school. And here I was, this novice graduate student, trying to read all the literature by some of you guys here, a lot of you guys here, and we read, and it was not a program in the learning sciences, it was more in technology, media, and cognitive studies. So we read a huge range of research on psychology, cognition, learning, how to design learning environments, and particularly how do you design scaffolds and support structures in these learning environments to help students accomplish what they may otherwise not be able to. And all that was great. I mean, they had research on hints and prompts and metacognition, reflection support, scripting, and so on and so forth, which is fine. But it kept nagging, based on the experience that I had, my own personal experience, both as a student and as a teacher, a couple of questions that just kept nagging at me. And these were perhaps very simple and naive questions. And the questions were, well, how do you know that the learner actually needs help? And B, how do you know what kinds of help? These are very simple, basic questions that as a novice graduate student I was asking of this literature. And I wasn't getting explicit answers to that. And so when I was talking to my peers and professors, they said, "Oh, Manu, we already know from a lot of work what students can't do. And we know they have trouble in collaboration, they have trouble working across multiple representations and other areas, and so on and so forth. So we know that, so instead of taking them through all over it again, we design these scaffolds and then we fade them away so that they can learn." I said, okay, that's a reasonable argument. If you already know the areas people struggle in, then you want to build those support structures in your learning environment. I said, wait a minute. Maybe, even if people struggle and fail at tasks in the absence of support structures, even if you know that, you might still want to engage them in struggle and failure, because what if, and this is an empirical question, what if that struggle and failure is actually beneficial for learning? And so that's how I started to think about failure. And this was about this time that the special issue of the Journal of the Learning Sciences came out on scaffolding. And that brought me into the scaffolding literature. And that was a really excellent special issue that also led me back to the seminal piece in scaffolding, which is the 1976 piece by Woodsbrun and Ross. And that article actually left a very deep impression on me as well. And allow me to just briefly share. It was a study with 3-, 4-, and 5-year-old children playing with wooden blocks that could be pieced together into a pyramid. Right? And the experiment started by an adult with a child, and the child was just allowed to play. The child perhaps didn't even know, if I remember correctly, that you had to build a pyramid out of it. He was just allowed to play. But the adult, looking at the child's performance in relation to the goal of building a pyramid, if after those 5 minutes the child did not do anything, then the adult will pick up a couple of pieces in the field of the learner, put them together and just leave it. Right? And the child picked it up, then the person would signify that as something as important and slowly scaffolded the child to build the pyramid. And it was important in very significant ways for me, because this is when I realized, again, think of it as a novice green graduate student, that failure is actually at the heart of scaffolding. Like, unless you have information about what people cannot do, unless you have some design for failure, you do not know whether the person needs help and exactly what kinds of help the person needs. And then that's when I started my program of research, the initial thinking that went into building a program of research on productive failure. Well, I hadn't, like Michael said, even late on in my graduate days, I hadn't come up with this title. It was actually on a drunken Friday evening that this happened, but that's another story. So really what I want to share with you is, against that backdrop, I want to share some research that more broadly, not just learning sciences research, but more broadly, that I will try and build a case for failure. But briefly, then I'm going to share what productive failure is all about and what designing for productive failure looks like. I'm going to share with you a series of studies that have done on productive failure, investigating little different things. And we'll have time for some discussion and implications. And I hope you'll ask lots of good questions and tough questions at the end of it. Okay, so the case for failure. There's a whole body of literature. I'm not the first one to think about it, and nor would I be the last one to think about it. There's a whole body of literature. So let me start with research in cognitive strain and disfluency. I mean, this is outside of the learning sciences, but there's a whole history of research on how even superficial changes in text and font, how they can make that they increase the load, but they also invoke compensatory processing that helps you remember and recall what you're reading. It's not just in attention and recall, but it's also in problem solving. So like tricky problems like, if 5 people paint 5 walls in 5 days, then 100 people would paint 100 walls in. A lot of people would say 100 days, but actually it's 5 days. And people have shown that if you could just change the font or even do some superficial changes to the phrasing of this problem, that people pay more attention and are actually able to see the trick for itself. So even in problem solving, there is a lot of psychological research that shows that designing for cognitive strain or disfluency, that it's being now called, actually, although it increases the load, it actually is better for attention, memory, and recall, and even problem solving. So this is already out there. And we had a perfect demonstration yesterday as well, with Michael in his small fonts. It was a very clever ploy to have us pay attention, right? And that's precisely, and I'm sure if we did a poll of what people can remember from the front of the room to the back of the room, we'll see a nice experimental demonstration of what people can remember from that. Okay, so that's already a body of research that's been going on for years. Margaret Clifford, who wrote a couple of really nice pieces in Educational Psychologist in 1978 and 1984, and she called for a theory of constructive failure. But she was coming at it, she was investigating failure from the lenses of frustration theories, reactance, attribution theories, motivation. So she's coming from that lens, and she reviewed a host of controlled experiments on how failure can be designed for learning and how it could be beneficial. And basically her conclusion was that you don't want 100% success, neither do you want 100% failure. But some moderate levels of failure might actually be good for learning. And so she challenged the maxim that nothing succeeds like success can actually be doing more harm than good. So this was already 1984. And then we have desirable difficulties that a lot of us are familiar with in psychological science, Schmidt and Bjork's work. Although they didn't cite Clifford's work or earlier work, but they were coming at it from a different angle, from training. How do you acquire something in training or learning phase, and then you apply it later on? And they reviewed a host of motor learning and verbal learning literature, again, randomized controlled experiments, to show that, designing for certain levels of difficulties, be it in terms of variation, task complexity, delay of feedback, and so on, can actually hinder performance in the shorter term, but actually can be productive for learning in the longer term. And hence the notion of desirable difficulties, learning. So these three bodies of literature have been very influential, at least for me, and I've read them very carefully, and they are randomized controlled experiments, which seem to be the gold standard in terms of what counts as scientific evidence for a person who does classroom-based research like myself. And there's Kurt Van Leeuwen's work on impulse-driven learning. This is on one-on-one tutoring situations, where he found that the likelihood that an explanation will have impact or will lead to learning, the likelihood increases if that explanation comes at the point in time where the learner is at an impasse. Right? And so again, it's when the learner gets stuck or it's at a failure point that if you provide that explanation or feedback at that point, then it's likely to be more productive for learning. So that's in one-on-one. You have Kedinger and colleagues have done excellent work on the assistance dilemma in cognitive tutor environments. So that work is already out there. And of course, in classroom-based work, we all know Dan Schwartz and Bransford and Taylor Martin's work on preparation for future learning and inventing to prepare for learning, how structured invention activities can actually be beneficial for learning. So here is a host of studies across different disciplines. And Janet, I hope this passes the more than 3 test. Okay. So it's not just learning sciences research, but a wide variety of research that shows that how designing for failure, maybe not all of them foregrounds failure, or it talks about it in that sense, but collectively they're pointing to the role of failure in learning and problem solving. And my work simply builds on this body of knowledge. So what is productive failure? And in a very simple way then, it's really about trying to understand what a learner knows by giving the learner a very complex, challenging problem to solve, so that learners' prior knowledge gets activated and differentiated, and to the extent that the learners can generate, explore, critique, and refine iteratively multiple representations and solutions to solve that problem. And we know that because they haven't been taught or learned that concept in the formal sense, and we know that we haven't supported them in any way, that this process is will likely lead to failure. And of course, failure in relation to a particular goal. And here the goal is to understand that concept formally in the canonical sense. But we need this information of failure so that it can be a locus of deep learning, powerful learning, provided you use this information, just like in the scaffolding literature, to build upon and actually provide some kind of structure in a variety of ways that can make this so-called failure into something that's productive. And that's where the design comes in, which is in a recent paper at the JLS. And thanks to Kate Belacek, who forced me to think about designing, the design principles. And basically we have a 2-phase design, a very simple design, a generation and exploration phase, where we give students these challenging, complex problems, and we have principles for designing these tasks as well. We get them to collaborate, and all we set up appropriate expectations and norms within which this activity is going to take place. Right, but we don't provide any cognitive or domain-specific support or scaffolds in this process. Okay? And after they've done that, we provide consolidation. And this can happen in many ways. I've tried at least a couple of different ways, but it's open. We can try it in different ways. So in my PhD study, I provided the consolidation in the form of well-structured problem solving. And in some of the studies in Singapore, I've provided the structure in consolidation in the form of direct instruction or teaching. But it can be in other ways as well, like feedback or providing explanation or reading a canonical text and so on and so forth. And so you can see that there is this delay of structure. So it's not that you don't give help or you don't provide structure, but you withhold it until such time the person has struggled and failed in solving these complex problems, and then you come in and provide that structure and support. Okay, so it's not whether if you should provide structure, but when and what kinds of structure, and that failure gives you information about how to support it. Okay, so my initial work on productive failure was a randomized control experiment in Newtonian kinematics. I put students into groups of 3 triads, and we gave them 2 kinds of problems that targeted the same concept of Newtonian kinematics. And these problems were either well-structured problems or ill-structured problems, and students were working in an online environment, in a simple chat environment, trying to solve these problems. And what we found was that compared to the well-structured groups, the ill-structured problem-solving groups, they had to generate multiple representations and methods, multiple ideas, multiple ways of framing the problem, multiple ways of trying to think of solutions, and so on. And we also found that they engaged in more complex interactional patterns of analysis, critique, evaluation, back to analysis, solution proposal, whereas well-structured groups did not have to do that. We also found that the ill-structured groups have very low convergence in their discussions. And so not only were the interaction patterns more complex, they were more divergent as well. And it was not surprising then that if you look at the actual quality of solutions that students produced, that the quality of solutions produced by ill-structured groups, the group performance was significantly poorer. And at this stage you can say, well, this is to be expected. You don't provide support, you don't provide any structure initially. Of course, the ill-structured groups are going to fail. But what happened interestingly afterwards was we gave everybody individual problem-solving, well-structured problems. And these were isomorphic with the earlier one. And then after that, we gave everybody extension problems on a more advanced concept. And these were all ill-structured problems. And that's when the productive failure effect came. That is, when we look at performance on the well-structured problems, individually, the middle section, we found that students from ill-structured groups outperformed those from the well-structured groups in solving the very kinds of problems that they had succeeded in. And so that was a very interesting finding for me. And that went onwards to the ill-structured problems as well. And the trick here was, at least how I thought about it, was there was this delay of structure. And really what was ill-structured about the problems was that the deep structure of the problem was not discernible. Because once you get the deep structure of the problem, then it's very easy to solve it. And so that contrast between an ill-structured followed by a well-structured problem, that gave them contrast, and that was when they saw the structure and they could solve it and they just got it. That's my explanation for it, and at least that's how I put it across in that paper. So that was the initial work on productive failure, initial experiments on productive failure. We looked a bit further into it. We wanted to ask a couple of questions. Well, can variation in individual or group prior knowledge, is it the case that perhaps students started out with different kinds of priors in physics? Could that explain some of the findings that we were getting? We also wanted to see whether there was variation in group performance. Yes, on average, the ill-structured groups did worse than the well-structured groups, but there was still variation within the ill-structured condition. So maybe some of that variation, maybe some of that variation could explain. And the answers to both these questions were no. That does not. So where you started out in terms of your priors and where you ended up in terms of group performance, it did not explain. What really explained was really the complex interactional dynamics that the groups had to go through. So it's really the exploration, it's the generation of the multiple representations and solutions, and the exploration of the problem and solution space. That's what made the difference. And we built a model using lag sequential analysis, which is what we presented in a paper in the IJCSCL. So thank you, Jerry, for supporting that. So that's where this PhD work was, and that's how I got out of graduate school. And then I came to Singapore. And Singapore has been wonderful, especially if as a young researcher, an early career researcher coming in with some ideas. We have great access to schools, a lot of funding. You can really run with your ideas very quickly and build a program of research. So that way it's been really, really nice to be in Singapore. And then we have really great people in the lab as well. So And yeah. Okay, so what we're now doing is, and this is analysis in progress, and it's one of my favorite bits of analysis. This is deep qualitative analysis of trying to understand, yes, the productive failure on average works better than the other condition, but even within productive failure, there are groups that are not quite productive. So we want to understand what is it that makes productive failure fail. Yeah? And the preliminary findings that we're getting from the qualitative analysis is that while groups are going into this divergent exploration of the problem and solution space, what really makes a difference is if this divergent exploration is driven by a meta-strategic or an epistemic convergence to do that kind of divergence. It's like that convergence at a higher level is actually driving the divergent exploration. And that's what makes good productive failure, and when that does not happen, productive failure fails. Well, that's the initial idea or the initial analysis, but this hasn't been written up just yet. Okay, so now this is Singapore work. I'm working in math classrooms. Before I share more of the experimental work or quasi-experimental work, I want to give you a chance. I want to give you a good sense of what it is that students actually produce when you throw them into the deep end and get them to solve these challenging, complex problems. So here's a unit that we've worked with grade 8 and 9 students in Singapore across different ability profiles. And the topic is on standard deviation or variance. And we've got them to, instead of teaching them up front, we say, well, before we teach you, we want you to design or to generate as many measures of consistency. So take this data and generate as many measures of consistency as possible. Now, some of you have seen this data, so please don't participate right now. But the others, can you sort of guess or estimate what might students do? Students who do not know stats in terms of standard deviation and that kind of knowledge, or haven't learned it. In Singapore, they only learn it in the 10th grade, so at this age, they definitely do not know it. So what do you think students might do when they've been asked to do this? Any ideas?
Max and min.
Maximum and minimum, yes. They might take the range. They might not call it the range, but yes, they consider the max and min. Any other ideas? Oh, come on. I'm sure you have ideas. Terry? Did somebody say the average? Yes. Okay. Yes, they definitely do averages. Yeah.
Count number of values.
Count.
How many distinct different values are
Yep. Yes. They do that too. Look for the mode. Yes. The most frequent number. Yep. Maybe use some bar charts to see the distributional information. Yeah. Very good. Yeah. Oh, wow. Okay. So that's that happens like 1% of the time, because that's already students do not know that concept. But actually, that happens if the concept of mean was taught in that way. You know that the mean is the point where differences from the mean actually cancel out. So if people have been taught the concept of mean that way, then they're likely to develop that. But usually, it doesn't happen. But thank you. There's another idea somewhere here.
Whoever has the most scores with the same number. So if I've got 4 11s and that person
Right.
has got 3 14s.
All right, good. Yeah, so counting how things remain similar or same or do not change. Yeah, yeah.
Something close to the median.
Something closer to the median. Okay, good. All right, so now, I mean, that was a great selection of ideas. And every time when I work with teachers and during their professional development to prepare for productive failure implementation, this is what we go through anyway. And so it'll be interesting to see what students actually do. And what I'm going to share with you are not ideas or the representations and solutions that like high ability students have generated. This is average students in Singapore generating this kind of work. So let's have a look. So yes, they do mean, median, mode. But we've designed this, and this is part of the principal way in which we design these tasks. We've designed this task to keep this invariant, so that we know that they're going to use averages, mean, median, mode, but we've designed the problem that while it invites them to use that method, but it's not solvable using that method. Okay? Same for they start counting and do frequency tables, and they're able to say, look, if you compared the last person, Ivan Wright, then he's either very good or very bad. So that's not very consistent. Between the other two, you can start to see that Dave Backhand is getting a little bit more bunched up. And you're right, they do dot diagrams and bar charts, again, looking at the thing qualitatively, and some of them even do box plots if they've learned that. You know, they do fluctuation graphs, or, you know, and you ask them, what are you doing? And they say, oh, well, if it goes up and down a lot, then it's not very consistent. But if it doesn't go up and down a lot, like it's smaller, then it is very consistent. And I say, yeah, that's good. Can you quantify that? You know, can you design a measure? So this is good thinking, but go on, think of another way of building upon this way and designing a measure out of it. They start counting. Children love to count, and one of the very popular methods that comes out is they count how many times a person scored above the mean, at the mean, and below the mean. And either qualitatively or quantitatively, that can tell us that consistency is simply a ratio of how many times you were at the mean divided by how many times you were away from the mean. And actually this is quite reasonable, because if this ratio is high, you're more bunched at the mean. Whereas if this ratio is low, you're away from the mean. It's a very reasonable idea, except it doesn't tell us how far above and how far below, but in terms of mathematical thinking, this is a really clever idea. And some people build upon this to work with intervals and so on. Okay? Minimum and maximum, so that's good, range, but again, we know that they might do that. We've kept the range the same, so that they can't use that method. It's sort of the evil side of productive failure. A very popular method to quantify the fluctuation graph especially is to think of consistency in terms of year-on-year deviations. So they calculate, so you have the data stream, and they'll take year-on-year deviations and say if you can sum all these deviations, the total gives you a sense of total change in the data. Year-on-year change in the data. And that's a measure of consistency. And again, you're beginning to see that the ideas of deviations from a particular point, adding all those deviations, these ideas that go into thinking about variance mathematically, and these are already embedded in some of these solutions. Some of them realize that, well, it's not fair. They have a very unique sense of fairness, that it's not fair that positive and negative deviations are cancelling out. Again, we haven't told them anything, but some of them realize this, and they ignore all the signs. Still year-on-year deviations. And someone said, let me get an average sense of what the change is, and they divide it by the number of intervals that for the deviations. And so they do get that. And like I said, deviations from the mean is very, very rare. And that's understandable. Nor do we expect them to be able to develop deviations from the mean. And from time to time, we get some really creative solutions, and I'm going to show you one. And this is when they were trying to quantify the fluctuation graph. Now, I'm not sure if you can see this at the back, but I'm going to describe it. And this group of students said, imagine I could take the graph and stretch it out into a rope. And if I could somehow find the length of that rope, then that would be a measure of consistency. Because the longer the rope, the more inconsistent. And the shorter the rope. It's brilliant. I mean, again, this is not typical. The rest of it is typical. This is not typical. But I just wanted to share the kinds of possibilities that can emerge once you give students these opportunities to solve challenging problems. And they've learned Pythagorean theorem in primary 6, in grade 6. And what you see there are Pythagorean hypotenuses calculated for each year, because these are all right-angled triangles, to calculate the length of that metaphorical rope to calculate consistency. Okay, and so and we have other creative solutions as well that emerge from this. But the idea is, what's happening is, like when you give students the opportunities to do this, it's activating their priors. It's differentiating. They're thinking about the concept that they're about to learn in different ways. And some of them are suboptimal, some of them may be incorrect, but it's important that we get them out. And by comparing and contrasting these representations and solutions, you're bringing attention to critical features. I mean, even without telling them or without teaching them anything about standard deviation, just by contrasting and comparing these student-generated representations, you can talk about the difference between the center and the distribution around the center. You can talk about qualitative and a quantitative measure. You can talk about why must deviations be positive? It's already there in their solutions. Why must we add all the deviations? We've got methods where multiply. But of course, if one of the deviations is 0, the method does not work. So we've got that discussion that can happen. What is the need for a fixed reference point? Why must deviations be taken from a fixed point? And why must that fixed point be the mean? Why can't it be the minimum or the maximum? These are exactly the kinds of discussions that you want to have. And this student-generated representations and solutions set the foundation for that kind of consolidation and teaching that can happen subsequently. Right? So that's what students can do, but it still remains to be seen if engaging students in these long sort of design generative tasks is actually effective for learning. So we've done a series of experiments, quasi-experiments, classroom-based experiments on two topics, an average speed and the one I showed you in standard deviation. This is the most recent data, and that's why I shared it with you. And generally our tack has been to compare it with a design that's most prevalent in Singapore schools at least, and that's direct telling. So if I'm supposed to teach you something, I'll explain the concept, model the problem solving, use some worked out examples, and then give you some practice and so on and so forth. So that's like a very common design that at least in Singapore is very prevalent. And then we have productive failure, where instead of teaching them first, we give them this task, and that's what they do when we give them that task. Okay, so that's like the broad design. And we measure different kinds of things, learning in different ways in terms of procedural fluency, which is simply, can you calculate something and can you interpret the values in a problem-solving scenario? Conceptual understanding really relates to those conceptual features that we talked about. Do you really understand why the formula or why the measure is the way it is? And then transfer. Can you use what you've learned and apply it to solve a problem that requires a more advanced concept? And here, like for example, in standard deviation, we had taught them about standard deviation, and then we asked them to solve problems on normalization, for example. So questions like, is Usain Bolt a better champion than Michael Phelps, or something like that? And that's a very different way of flexibly adapting standard deviation to solve that problem. Or in the case of average speed, we had them solve problems on relative speed. So those were the kinds of transfer questions. And so every time we've done this, and in Singapore, we've been able to do this across ability profiles, and we found that invariably PF performs, productive failure outperforms direct instruction, especially on conceptual understanding and transfer, without compromising procedural fluency. So teachers are assured, at least, that the basic stuff that comes out in exam is not compromised. And that's a good thing. Of course, it raised the question that if productive failure groups can do so much, even without any support, might not support actually make them go even further? So we designed a study where we provided cognitive prompts and explanations or hints to further their generative generation and exploration phase, and we found that the marginal gain of providing that kind of hints and prompts that will help them in the generation phase actually is not significant. And again, this is just one study and one way of providing support, but that does not mean there are other ways that may not work. In fact, that's one of the areas that we are looking at as part of our future work. Teachers, being experts in mathematics, or perhaps as a function of being experts in mathematics, consistently, bad choice of word, but consistently underestimate students' ability in terms of what they can produce. And a lot of their estimates of what students can produce are actually from the textbook. It's very hard for them to imagine, and I think it's understandable. It's very hard for us to imagine unless you actually give students these opportunities that they can actually produce what I showed that they could produce. This is something that it's in the Singapore context is especially nice, is when you take students. Now, let me back up. We have a grade 6 high stakes national exam, okay, which is called the Primary School Leaving Examination. That's the PSLE. Okay, and that determines, your score in that exam determines which kind of school you go to. So we have a peculiar situation where if you look at the secondary schools, the grade 7 onwards, within school variation is very small compared to the population variance. So in terms of sampling, if you want to test something out, you need to sample across different types of schools to get a sense of what it might do in the population, if there's any sense of representativeness. Because within school variance is very small compared to as a function of the streaming that happens at grade 6. So because we've been able to do this work in different kinds of schools, high on PSLE, average on PSLE, I find that if you start with students who are strikingly dissimilar in terms of their general and math ability on a math score on the PSLE, on the scientific exam, and you give them the same task that we've been giving them, and you compare what it is that they can produce, one would normally guess that students who are high on PSLE should do a lot better, or proportionately better, in generating representations and solutions than students who are low in terms of their general academic and math ability. And it turns out that is not the case. I mean, sometimes there are still differences, but these differences are significantly reduced. So you're starting out at extremes, and you find that students actually have very good generative capacities to generate solutions to challenging, complex, novel problems. But that alone is insufficient. I think what's interesting is that what students produce, the number of even a simple measure such as the number of different representations that they produce, is actually correlated, significantly correlated with how much they learn in terms of their conceptual understanding. These are significant correlations. So it's not the prior ability or prior ability differences that are predicting how much you learn from PF. It's the ability to design RSMs, representations and solutions to these problems, and the more you can do that, the more you learn. And that to me is a very promising finding, especially in Singapore schools. And a consistent feedback again we get from teachers is that that they're very stressed to work with these ideas, because it pushes their own content knowledge in ways that they've never experienced it. And I was hoping that they'll say, oh, I really enjoyed productive failure, I know this new way of teaching, but we don't get that kind of feedback. What we get is, oh, you know what, I now understand the math better. Which is kind of nice as well, that teachers themselves feel that, as they're teaching in this way, they're learning more math. In fact, we've got comments like, I never understood standard deviation or average speed like I do now, which is nice. Okay, so very quickly, again, what's happening here is student knowledge is being activated, it's being differentiated. There are more opportunities to attend to critical features. They're collaborating, so they're explaining, critiquing, and refining, and elaborating upon each other's ideas. Ownership came out as a very strong factor that from PF groups, because they've generated 5 to 6 different representations. Then they want to know, so what is this canonical idea? How is it so much better than what I have? And so students own these representations, but this is just qualitative analysis that we've done. They're becoming flexible and adaptive, so just when they produce something, they know that they have to refine it and produce something else, and they keep going. And of course, it's not a case that we have this one size fits all for all the different schools. We developmentally calibrate how much and for how long and what ways can students persist in these tasks for different kinds of schools. Okay, and invariably after the generation and exploration phase, I'll go up to some students and say, so what do you feel about this activity? And one of the things that comes out is, we felt that we were like mathematicians. So, which is also nice. Like, they're not just learning about the mathematical concepts, but they're also learning mathematical thinking and what math is all about. So that's what's happening in productive failure. Now, if student-generated representations are important, then do we actually need students to generate these representations? We know they're correlated with learning, how much they learn from productive failure, but do we actually need them to generate? Can we not now that we know what students can produce, I just showed it to you, can we not convert them into nice worked out examples and get students to study and evaluate them? Why must they generate? Why can't they just study and evaluate it? Or in common parlance, I say, yeah, okay, we can learn from our own failures, but can we learn from the failures of others? Or vicarious failure, in other words. And there's an old Chinese proverb, they had it thousands of years ago, and it goes something like, intelligent people learn from their own mistakes, but wise people learn from the mistakes of others. And I would imagine the wisdom is rarer than intelligence. And so predicting, based on the Chinese proverb, that productive failure should be more likely than vicarious failure, because it's harder to learn from the failure of others. And that's I'm going to show you a study that builds on Ido's work on vicarious failure. I keep calling it flavor for some reason. And the second point is, right, so, having generated all these RSMs, it really affords attention to those critical conceptual features. Well, now that you know what these features are, why don't you just directly teach it to the students? Why bother? What's the benefit of having them generate and then discussing these features that are important? But now that you know these deep conceptual features that are important for understanding the concept that you're targeting, why not just directly teach that? Okay, and do away with generation altogether. So here are two studies I'm going to show you in succession that answer each of these questions. So again, this is recent work, quasi-experimental work in Singapore schools. Productive failure condition is exactly the same as the one that I showed you, and the vicarious failure condition is simply that students are no longer generating those solutions, but they are given peer-generated solutions to study and evaluate. And because we know that evaluation can go both ways. On the one hand, you can say, well, they just have to read and understand, and so they know all these different ideas, which will prepare them for learning later on. But on the other hand, evaluation, requires some expertise, and it could be a hard thing to do. And in fact, we know from some, like Ido's done work where when he's asked for evaluation, students are not really able to give proper explanations. So we provided them with some training as well. We showed them a contrasting case where what makes a good evaluation versus what makes a bad evaluation. And even with evaluation training, they were able to, they were able to produce some valid evaluations. But even then, when you compare the results on the same kinds of variables, the effects are reduced, definitely. But you still see that learning from your own failure, productive failure, is actually significantly better in terms of conceptual insight and transfer than vicarious failure, which are the greens. So the reds are productive failure and the greens are vicarious failure. So preliminarily, it seems that the Chinese proverb was indeed true. In the second condition, the second experiment, just to back up, sorry. So in all these experiments we've done with high and average ability students on the PSLE, and the results are quite consistent. Okay? And here's a strong, I'm just calling it a strong direct instruction, so that when the teacher teaches a concept, they actually pay attention to all those 8 or 9 critical features. And so as they're explaining and modeling the solution using standard deviation, they're actually addressing these features explicitly in their teaching. And then when you compare that with productive failure, how do results stack up? And what we find, the effects are drastically reduced. In fact, the effect sizes are substantially lower now. So the point is that if you can design good direct instruction, it actually is not such a bad thing. But if you really want even deeper conceptual understanding and transfer, then you're looking at things like productive failure or other methods. So that directly teaching critical features is actually it actually significantly improves learning as well. Okay, so where are we going with this in more recent work? It's one of the things that we want to do is to unpack some of the design components. We want to look at more closely the role of prior knowledge. Now, a lot of this work, a lot of the challenging scenarios that we develop for students are experientially grounded, whether it's Newtonian kinematics or consistent striker or average speed. These are experientially grounded concepts, and therefore it's easier for students to generate representations and solutions. But what happens if you move to scientific domain, multi-level phenomena, which happen at the cellular, molecular level? The students don't have access to that phenomena. Can we still do some things like this? Can we still get them to generate if they don't have access to one part of the phenomena, but they can think about at the macro level? So these are ideas, and maybe it's possible, maybe it's not possible, and that's some of the work that my doctoral student, Leslie, is going to share later on today. We're also looking at the role of the teacher, because not all teachers do the consolidation as effectively as one would imagine, and so there's variation. So what do teachers do that's effective that's good for consolidation? The role of collaboration. Could it be that it's because people are collaborating that they're able to generate all these different representations and solutions. Might individuals do better or worse? In fact, some of the preliminary work we find is that sometimes individuals do a lot better. The collaboration on average is good, but the best individuals are way better than any groups, you know. And so we're unpacking that effect a little bit more. We're also, like I said earlier, right now we're not providing extensive support to scaffolds as students are generating, but there is research coming out on metacognitive scaffolds and other ways of designing scaffolds that may not be content related, but help the groups perform better in terms of collaborating and generating ideas. And we're trying to explore if that can further enhance the generation and exploration phase. Like I said, we're examining different ways of consolidating after students have generated. We're also examining the effectiveness in other domains. I mentioned science, but also math and science tend to be very well structured domains. Can we move this into other areas such as writing, and so on and so forth? And we are exploring some collaborations on that, and if you're interested, please let me know. But among these, the most exciting for me is that we're moving into research and problem finding. I mean, as a cognitive science and learning sciences, we understand a lot about, given a problem, how do people solve problems? It's problem solving. Whereas, how do these problems come about in the first place? You know, it's the role of failure in getting students to think about generating problems that are worthy of solving. So ask and answer kinds of questions. So we're designing productive failure studies in problem finding contexts and comparing them to problem solving contexts. So, and that's something we've just done a couple of studies in that, and that's where we're going with this. Okay. Okay. So that, in a nutshell, is basically 6 years of work. Right, and where we're going with it. And I wanted to, towards the end of, how am I doing for time? Yeah? Okay. Towards the end of I wanted to speak a little bit about cognitive load theory, because I've had several run-ins with cognitive load theory. So I thought maybe but I'm going to talk about it in a very dispassionate way. I'm not for or against, but I really wanted to understand what the objections were. So let's start with this and see where it takes us. So we all know, Paul, you're here, 2006, there he is. Paul and Sweller and Clark came out, the educational psychologist article, and said something like, among other things, that controlled experiments almost uniformly indicate that when dealing with novel information, learners should be explicitly told what to do and how to do it. Now, immediately, if you look at just the research within worked examples, it seems to be true. But the moment you go beyond to the larger psychological research, the one like even cognitive strain, cognitive dissonancy, desirable difficulties, this doesn't hold true more generally. It may hold within that field, but it doesn't hold true more generally. But their argument is basically from the cognitive load theory perspective that unguided or minimally guided instruction increases the working memory load. And because working memory capacity is finite and limited, it interferes with schema acquisition. So high load situations should interfere with learning, basically. And they have tremendous empirical evidence when they've compared some kind of a worked example or strongly guided instruction with pure problem solving or a discovery kind of condition, that students in the worked example or strongly guided instruction always do better. And these are randomized controlled experiments themselves. And then there's a conclusion that, there's little efficacy. Why bother getting students to generate these ideas and representations and solutions? And there is absolutely no efficacy in doing that. But my point is that, yes, it's not surprising that if you compare those two extremes, that you get students in the direct instruction condition doing better. Now, of course, there are a couple of studies that are exceptions to these rules, where they have explored not just discovery conditions or pure problem-solving conditions, but the bulk of the literature is largely about comparing these two extremes. Because if you really want to look at whether there is an efficacy in getting students to generate solutions to concepts, to problems that target concepts they have not learned yet, then you need a stricter comparison. You need a condition where students first generate but then they're provided with some kind of structure later on, and not just left alone by themselves. Because if you just leave it alone, obviously nothing's going to happen. Sometimes they may discover something, but it doesn't happen very much, and very often. And which is what productive failure work has been about. And also earlier work has shown that if you provide the stricter comparison, even be it productive failure or even vicarious failure, you get better learning than direct instruction. So what's going on? How is it that students, obviously when students are given this challenging problem to solve, the cognitive load is very high. So how is it that they're able to generate all these solutions? And how is it that they're able to learn from productive failure? So what's happening? And the trick is, it's actually within the cognitive load theory itself. Because Kirshner and colleagues go on to say that any instructional theory that ignores the limits of the working memory when dealing with novel information is likely to be ineffective. But that's only one part. The other part is any theory that ignores the disappearance of those limits is also going to be ineffective. Right? So really, the theory rests upon what is novel and what is familiar. And how do you decide what is novel and what is familiar to the learner? So novelty of information compared to, in relation to what the concept is. And so really it's an interaction between, if you take the commitments of cognitive load theory to itself, then you find that it's really an interaction between working memory and long-term memory. So how do you decide what's novel? So maybe you can think about novelty in the canonical sense, in the formal sense. They really do not know the concept of average speed as in mathematics, or they really do not know the concept of standard deviation as in formal mathematical idea. And therefore we assume that they do not know that the information is entirely novel to them, and therefore we must teach them. Because cognitive load theory tells us that any instructional theory that ignores the limits, that ignores those limits, is likely going to be ineffective. But we can also think about in the non-formal, informal ways, that yes, in a lot of these studies, students do not have the formal canonical knowledge, but they have informal intuitive ideas. If you can design tasks and activity structures that helps them, that elicits this knowledge, helps them think about and activate their priors about the concepts that they've not learned yet. And we've shown that students actually have these constructive resources, and we're certainly not the first ones. There's a whole body of math education literature that looks at the inventive and the generative capacities of students without having learned formal ideas. So we know that students are able to do it, provided we can design these problems and activity structures. And what we're really doing there is we're activating information in the long-term memory from the cognitive load theory lens and getting that to interact with the working memory. And so maybe, even if you take cognitive load theory to its own commitments, you can explain how a lot of the work that's gone within the worked examples literature has only looked at one side of the story. And that is assuming the students do not know the formal idea, and therefore we must teach them or provide worked examples or direct instruction. They've not looked at the other side, where if you can activate things in the long-term memory, that activation itself could be a basis to solve these complex problems and learn from them, even if it leads to failure. Right? And so I think there's more happening in productive failure than cognitive load theory can explain. But even if you take cognitive load theory dispassionately and hold it to its own commitments, you find that there is certain work that still can be done. Yeah? So, in ending, there's this incommensurability between learning and performance, like what Schmidt and Bjork talked about. You know, sometimes learning and performance are incredibly well aligned. You know, high performance really leads to high learning, so we call it productive success. Right? All I'm saying is failure is not a necessary condition. It is just that it can be productive for learning. So, by all means, if students are able to generate and successfully solve these problems or somehow discover the canonical solution, that will still be good learning. And we call it productive success. So the high performances and high learning go together. But there are also cases where performance may dip in the shorter term. They may not be able to generate the canonical solutions, but they learn more. And that's productive failure. What we don't want is unproductive success. An illusion of learning in performance. And when I share this with teachers, that's an idea that they get it. Because that's an immediate reflection of the thing, oh, maybe that's what that's what's happening in my classrooms a lot. There's a lot of focus on performance without learning, or deep learning. And what everybody doesn't want is unproductive failure. No learning, no performance. And I certainly hope that that hasn't been the case in this talk. Thank you. Oops. There you go.
Well, we clearly have time for questions, so hopefully they will be productive.
Yes. I think.
I can.
Okay.
Yeah, you can run it around. Yeah.
I really enjoyed the talk, and I very much like the idea of the productive failure. I think what I want to bring up as a question is, when I think about applications to science learning contexts, and I think about problems that are not as well defined, like a problem that we've been looking at problems that kids are working on essentially for 6 weeks, let's say, trying to figure out how, one example, trying to figure out how odors can travel across a room. What is it about the situation? What is it that they're traveling through that causes them to move, et cetera, et cetera? And the goal of which is to get the kids to work on an understanding of the particle nature of matter. The situation there, I think, is a little more complicated than just productive failure followed by the structure. What we see is kind of an intermediate state where so productive failure, in my view, doesn't mean working absent the teacher or any scaffolding. What we see is a productive period of time where they're trying to figure stuff out on their own. Then the teacher comes in at some point and asks really hard questions that play a sort of problematizing role that focuses them on productive issues to worry about. And then they go back and worry more in their groups and try and figure out some more without having been given all of the structure and the canonical answers and so on. But the teachers focus them on that parts of the issue which they wouldn't see as problematic. Like what's in, you're proposing there are these particles, but what's in between the particles? And the kids realize that half of them think air is in between the particles, half of them think nothing is. The kids that say nothing, the teachers, at least in the effective situations, say, well, what do you mean by nothing? And then again, half of them think nothing means air, while the other half think nothing means actually nothing, etc. So it's not that there's unproductive, unsupervised, totally on their own, followed by that structure. What we see is some unproductive, unsupervised, followed by teachers coming in, giving them really hard questions, focusing in on productive things to worry about, et cetera, et cetera. And so it's a more subtle. I worry that people will misunderstand and think, oh, so we should leave kids alone, let them do what they want, and then at the end we'll come in and give them the answer. And good teaching that we see, at least in the science context, is much more of this iterative, incrementally providing that guidance, then letting the productive failure happen, et cetera. So anyway, that's my extension of what you're saying.
No, I completely agree. I have no disagreement with that. It's like cycles of productive failure built into that larger activity, larger progression. Yeah, absolutely. And that's very consistent with how scaffolding should be, based on my reading of the literature. So, yeah. And your work on problematizing scaffolds in that special issue is very helpful. Thank you. Yeah.
I really like how you think of, I think of our conceptual ideas we've had in the learning sciences for a long time, and give it some of the most convincing experimental tests of those principles. What I'm not sure I get is why you talk about it in a new way as about productive failure. So for a long time, so the failure gets called out for special attention by you. So for a long time we've talked about in terms of kids learn better with authentic problem, and when they're challenged, and we call out prior conceptions. So I guess I'm wondering, is productive failure just the name you attach to that approach that we've had for a while? Or do you really think this is something new and that the failure deserves to have this special call out for special attention?
Yeah. So like I mentioned in my review, I mean, I'm not the first to talk about failure, but I'm foregrounding it and analyzing it in what students produce and relating it to what they learn. So yes, I'm foregrounding the role of failure, but a lot of the principles that are based are things that we know that are good for learning. So I don't make claims about, oh, this is radically new stuff, but I do say, yes, we need to look at what happens when students fail to generate canonical solution, how is student production related to what they learn, and so yes, I'm definitely foregrounding that. Over there. Sorry? Yeah.
Thanks for that fantastic presentation. Look, I can't help wondering whether the main benefits of productive failure might actually be due to the cooperative component of it. And I'm just wondering whether you've done any studies where, rather than comparing to direct instruction, you're comparing to one of the sort of classic cooperative learning design patterns, perhaps beginning with a conventional instruction followed by some sort of group investigation or peer tutoring approach. Yeah. Or alternatively, whether you've compared a more sort of individual-oriented productive failure without the group component with direct instruction.
Yeah. So we've recently done studies comparing individual and group work in the generation and exploration phase. And the findings that we have from the math studies, and my doctoral students also working on it in biology, but the ones that we have from the math studies, the findings are mixed. So we have the effect where, and I think alluded to it in my presentation as well, where some of the best individual efforts are way beyond what groups can produce. But groups on average are better. So yeah, so there's a benefit to working in groups if the group collaboration goes well. But if you're really good and innovative and creative, running with your own ideas is also quite nice. And so we've done some of that, and that's experimental work, but I haven't got the findings out just yet to talk about it in a very systematic way. But yes, we are running those experiments, but not the first ones that you mentioned, though. Although that might be nice to consider as well. So thank you. Oh, there's so many. I don't know where to take. I think Okay.
Sorry. Just a question again about the failure part. If you had compared two groups who are working in this very inquiry-based collaborative way, where one group ultimately came to generate the right answer, one group ultimately failed to generate the right answer. They were all doing the same sorts of very productive, generating a lot of different explanations type of work. Would the group that failed to come up with the right answer do better? So is the failure really critical, or are some of these other components more of the central mechanism that's driving the learning?
Yeah, so that's like what I would call productive success. So I'm not saying failure is a necessary condition, just that it can be productive for learning. So if it should happen that students actually generate the correct answer, then I expect that they would learn. Yeah, but we haven't had a case, at least in the work that I've done, where actually one student has been able to generate the mean absolute deviation or the actual additive concept of average speed or standard. They haven't been able to do it. So I don't have data that I can compare. Or maybe I should do a study with a concept where there is a greater likelihood some students would be able to generate the correct solution and some students not. So maybe it's a choice of unit or concept that determines that. But in this studies, I wouldn't be able to answer that question, but only recognize that failure is not a necessary condition. Yeah. Dora?
I have a question about these terms, success and failure that we're using here. And correct me if I'm wrong, but it seems to me that these words are evaluative from the perspective of the educator. And I wondered whether it seems important to you that the students themselves are those who recognize their exploratory solution process as productive or unproductive. And I'm just thinking kind of anecdotally, because I don't study this directly, but cases where children work on combinatorial analysis where they were trying to figure out how many different ways to arrange something. And they themselves came and told me, look, this is not working and this is why. And actually by telling me this is why, they were articulating the very principles that I wanted them to learn, which was the systematicity and rigor. So it's important that children are those who decide whether their productions were successful.
Yeah. No, so, yeah, you're right. Failure is a value judgment based on comparing performance with a particular goal that you have in mind. Now, this goal may or may not be shared with the students. But in this case, it's from the canonical lens that there's this goal of learning this concept and getting students to generate. We've had the take that we have to set up appropriate expectations and norms so that students feel that this is something that is to be expected, that they will be asked to generate multiple ideas, and that it's expected that they will not be able to generate the canonical solution, but that the more they generate, the better. So there's this mathematical norms that's set up in the classroom when students are doing these activities. So you may argue, yes, that if you take the learner's perspective and really investigate, although we haven't asked them in that ways, what it is that they think about their own generation efforts, you may find a variation in terms of how students view their own generative, that process. And perhaps some of that variation could be related to how much they learn. So we haven't done that analysis yet. But yeah, the definition changes the moment you take a different perspective. Absolutely. Yes, Jeremy.
Thanks, Manu. I actually wanted to just make an editorial remark, a comment. I think you did a beautiful job of highlighting how this work really sits in and links to some past work. And I wanted to mention how I see it sitting in the future and relating to other work that's not necessarily productive failure, that this is a piece of. I see the key thing is we're starting to see complementarities between different forms of learning, where a lot of past learning science research was, is X better than Y. We're deeply investigating the nature of X produces learning. I just see many investigators here, I see great value in understanding how we can take different forms of learning and different ways of organizing instruction and put them in longer sequences that balance, complement, and in the end result in different learning.
Thank you.
Thank you. I'm very interested in the concept of ownership and then sort of coming to the canonical thing after that. Is there not a danger that students would really like their own solution much better than the canonical one because they've invested so much in it and they stick with theirs rather than the real one?
Yeah. I don't have data to answer that question, but that's a possibility. But if that was if that really played a very important role in how much they learned, then we would see them sticking to their own solutions on the post-tests. In much greater, a lot of students should be doing that if that was a plausible explanation. But we don't see that happening so much. So while it may still be possible that they're thinking about their own solutions, then I don't think that's necessarily a bad thing, because now they understand this canonical idea, but they also understand what are the other ideas and how they're related to each other. And
maybe there's some sort of effective step built in where you're saying, where there's not a sense of disappointment or got to let go of this thing.
Sorry, I didn't catch that.
There would need to be some sort of step where you're dealing with the affective issues around having to sort of let go of something like that. Right. Possibly, yeah. Ido, and then...
I'm afraid, though, we might need to cut the conversations off so that we have enough time for some caffeine and food. But I think that probably Jeremy's advice to Manu worked out quite well. I think we clearly have things to talk about, but more in the affirmative than in the other. So to that, I think we could thank Jeremy and also Manu for a very interesting, provocative, and certainly talk-worthy talk.
Thank you.
Put our hands.
Thank you.